Hey everyone, and welcome to this class, the LPS class. Today we will be again continuing with the Linux networking, lecture number 6. In the last lecture, we just introduced the DFS. Today we will be going on with the DFS, the distributed file system. In fact, I am going to actually we will start the DFS discussion today. Last time we just looked at some introduction, but I'm going to repeat that material again. Before I begin, I think we had a good lecture on the DNS system. We looked at the email last time. I'm not going to recap that today. If you have any doubts, we can always take it up in the next session or so. So let's begin the discussion on the distributed file system. Again, as I mentioned in the last class, we will talk about the distributed file system, what it entails, why is it a big deal. We'll go into the architecture. Again, we need to know like why it's a big deal again. What are the issues with the file system? What are the issues with the file system, and also we will take up like 2 case studies. One is on the Sun NFS system, and then the other one is Andrew file system. Again, let's see like how far we can get to, but these are the topics that I want to cover. So last time we discussed the file system. Again, the file system basically it was developed for a centralized computer system and the desktop computers. And file system is an operating system facility providing a convenient programming interface to the disk storage. So we will see like what are the gradations of the file system, or we have to understand the memory architecture before we go into the file system. And a distributed file system specifically, it supports sharing of information in forms of files and hardware resources across the network. So that is the key thing. And then once we have this distributed object system like Corba or Java in the web, this entire thing basically like how much we are sharing and how the sharing happens has become like extremely complex. So before we go into the storage system, let's look at just the memory architecture. I think this is something that you are familiar with. So we have say like this box represents the CPU, and then there is a cache memory which is part of the CPU, which is very localized, and in fact you won't even know the existence unless you look at the computer itself, or basically like what the chip has in the control panel or any other place basically. Typically these come in various sizes. Right now we have 1 gig, 2 gig. We all measure in terms of gig actually. Then we also have the main memory. This is an example, will be like the DDR memory. DDR3 is very famous nowadays. You get in 2 gig or 4 gig DDRs. Sometimes like even the caches it used to be like in Ks, now probably like in megs and gigs are also available. And the memory, of course, like main memory in a heavy duty server, it can go all the way up to like 1 terabyte also. Then you have like hard disk, which is essentially the storage where things get written, and basically it resides, the programs reside in the hard disk before they get executed. A distributed storage is nothing but so if you look at this particular box, the box around it is a system or a computer, and then basically like a distributed system is a centralized storage, and that is shared between multiple computers, or there are multiple disks that can be accessed by a single computer all through a network. So now, I mean, if you look at the hard disk and the distributed storage, apparently they are all the similar stuff. So what is the big deal in like using a distributed system? So let's look at some of the challenges. So when we talk about the distributed file systems, there are many challenges that that we need to overcome in order to make sure that we get we can reliably store and retrieve data. One of the issues is the transparency. So as you know, the data is written in various chunks basically. So what kind of data in a hard disk is transparent to the host systems? Is it all of them? Is it some portions are transparent to some of the systems and some portions are transparent to another system? How is that divided? And then when there is an overlap, like what happens? So these are some of the things that we need to worry about because there are many systems accessing the same disk storage. So again, that's one thing that we will talk about. Then the next issue will be the concurrency issue. What happens if two servers or two clients access the same files concurrently? Who gets the preference and why? So these are the kind of questions that we ask about concurrency. Then the other one is replication, which is when the file in a server changes, can all the clients see the change immediately, or do they have to wait? How does that work? So again, that's another thing that we will talk about. Then the fourth challenge is the heterogeneity challenge. Again, in this one is whether the file system support multiple OSs. So I'm connecting with Windows OS. Somebody else is connecting with Linux OS. Somebody else may be connecting with the iOS OS. How does the system behave in that sense? And does it support all the OSs or it supports some of the operating systems? How does it work? Then the other challenge is the fault tolerance challenge, which is when the file system crashes, how does the client know about that? Or if the client crashes, how does the file system react? Say like, I mean, you're writing to a file area and then the client crashes. Now what happens? To does that area gets recovered, or is it just called corrupted? What happens there? Then the other one is consistency. Consistency comes from the different clients when they access basically is that the what each client looks at from its perspective, are they all in consistent view? So that's another thing basically that we will talk about. And then the security is another concern. How do you authenticate a client or a user to a file system, and so that I mean only he can access. We saw like some of the high level issues regarding security in when we studied about the Linux, basic Linux OS, where we talked about the read write access, read write execute access. How does that work? So here we will be that challenge has been multiplied pretty heavily. So we will look at that. And then finally efficiency. How do we keep wastage of the space to the minimum? So are there techniques that we can employ to do this? What do we do? So again, as I mentioned, the classical examples are the Sun NFS and Andrew file system. So we will be learning about all these things. So before we go into that, let's look at the memory architecture, which is essentially we saw this in the previous slide. So let's look at it from the main memory onwards. So we are not looking at the caches and the inside whatever is inside the chip. So main memory, it's not share. It's not a shared memory. Mostly like it's local to that particular machine or that particular CPU. And the persistence, it's not persistent. So persistence is another property essentially for the data, whether when the process die, whether the data still stays there or not. So usually what happens is whatever the program that is running in a process writes out the data into the hard disk, so that the main memory is completely cleared of any of the remnants of that particular process. So so what that means is basically the main memory is not a persistent memory. So we don't keep anything after the process gets executed. Then by nature, main memory is also similarly is a very localized memory. So we don't keep any distributed cache or replicas. So that's also no. Then the consistency maintenance, again it tries to maintain the consistency, and the example essentially, but it's still a one copy consistency, so that you cannot replicate that copy across multiple main memory systems. Here we will call it main memory systems. Example is that RAM or the DDR is another one. So those kind of things. Now let's look at file system. File system, again, like you don't allow the file system to share, but it is persistent, meaning the data gets written into that file system after the process gets executed. Again, I'm distinguishing between program and process. This is the distinction that we saw very early in the course, which is essentially the process is a running instance of a program. I hope you guys remember. Again, the file system also doesn't allow distributed or cached replicas, because inherently, like this file system we are talking about is a file system within the computer, so it's mainly for that particular machine. Again, consistency maintenance is strictly like one copy consistency. Now let's talk about the distributed file system. This is where it gets interesting. We allow sharing in a distributed file system. The data is persistent, as we know, and then it also allows the distributed cache essentially, so that you can create replicas of data all over the place. And finally, the consistency maintenance is we'll have multiple copies which essentially go through that consistency. So we call it like approximate consistency. So we know that consistency is how each of the clients will view that particular files, and here it's almost there essentially. Some of the new information may not be there in the files, but pretty much like the copies are updated on a periodic basis. So now let's look at a web server. Web server also allows you to share the data. The data is persistent, allow the distributed cache and replicas, but there is no consistency. Essentially, like if something gets updated, everything is not looking at the same thing. So one data may be old, the other data may be new. Unless you hit like refresh, the data won't be updated. The distributed shared memory is another one. So here again we allow the sharing of the memory, but the memory itself is not persistent. The way that we allow the memory is also through the distributed cache and replicas, and then finally the consistency maintenance is also there. Remote objects, essentially this is something that the Corba supports. And again here sharing is done, and then it's just a one copy consistent. So if you look at it, so the highest one is probably the distributed file system, and then there's also the peer-to-peer storage system. which is also very similar, but the others are kind of, they are lower in the hierarchy, as you can see. The persistent object store and also the remote objects um, from the Corba. So let's look at the next picture. This shows like a layered module structure for the implementation of a non-distributed file system. So here we have a directory module, and then a file module, then the access control module, file access module, a block module, and a device module. So let's just look at what each the function of each of them. The directory modules is essentially like, I mean, that has all the file handles that are in that particular directory. So this is the each of the file IDs. The file handles are also known as the file ID. So essentially, the file names are related to the file IDs with using the directory module. The file module keeps all the file IDs and correspondingly like what is the file, where is it located, and all those details. The access control module is the permission checker. We already know that there are 3 types of permission: the read, write, and the execute. So the access control module is the one that checks for these permissions and whether certain operations are allowed or not allowed. The file access module, that essentially is used to read and write file data or the attributes, and the block module essentially like now accesses the file system or essentially the disk, and the goes and allocates the blocks that are needed for this writing the file, and then so basically like, I mean, the blocks are usually in chunks of some number, so that based on the file size or estimated file size, it allocates some blocks for that particular file in the memory. And then the device module is essentially like, I mean, now that is pretty much it. It is the module that accesses the disk, does the IOs, and also like does the buffering. So whenever you are reading the file, it takes the file ID, essentially like, I mean, accesses that particular disk, and it gets the file for through the buffers. It takes it through the buffers. Again, the file systems essentially like, I mean, so that provides the organization, storage, retrieval, naming, sharing, and protection of all the files. So a file contains the data and the attributes. So now let's look at how the file records are record structure or how a file record structure look like. So the key things that we want to write are the file length, and then it was created, a creation timestamp. If it is read multiple times, or when was the last time it is read, that's a read timestamp. After creation, when if it is written again, then the write timestamp, and then there are some attribute timestamps, and then the reference count. And then there are some additional ones, which is the owner, the file type, and then the access control list. So this is typically the record that is kept as part of the file, and we can actually access these various parameters to get to where what the value is. So these are done through the operations essentially. So let's look at some of the operations. So here the operation is open. Open is the name and then the mode. So it basically opens an existing file with a given name and then assigns the file ID to file destination. Create is another operation with the name and the mode, and this one creates the file with the name, and that ID is assigned to the file ID file des. So the mode can be like read write or read write, and then close the file destination or the file handle closes that particular file, any of the open files. And then if it can close, then it assigns the status as 0, and if it cannot close, then the status becomes 1. So based on the return value, we can decide whether the file got closed or not. And then the count, essentially, like I mean, this is actually like I mean the operation is the read operation, read file disk buffer n. It essentially transfers n bytes from the file to the buffer, and essentially like we can also like measure that in the count. Now the write, again file destination buffer n, will transfer the file, actually like I mean the n number of bytes are transferred from buffer into the file there. So these operations essentially like I mean they deliver the bytes, and they also advance the read write pointer. So the pointer is essentially like I mean what is in the file, so that you know like I mean where exactly that is. And then lseek is you give an offset and another param called when. Using this parameter, it goes and moves the pointer, the read write pointer, to that offset. And then unlink essentially like removes the file name from the directory structure. If it has no other names, it's just deleted. Otherwise, it's basically like it just removes that name alone. The other names are kept. And link name1, name2. Again, this adds a new name called name2 to the file name1. And then the other one is the stat command. This actually gets all the file attributes. We saw that here essentially in this one, the attribute count and then the attribute time step. So in all the attributes are it's taken and then put it in the buffer. So we already saw like I mean so the requirements itself, like I mean we know that these are the challenges and that's what we need. So let's look at the file service architecture. This actually offers a clear separation of the main concerns in providing access to the files, and it's obtained by structuring the file service into 3 components. So there is a flat file service, a directory service, and a client module service. So again, this the file service architecture is a way to organize the services that are associated with the files, so that things are provided properly. So now let's look at the modules in the file service architecture. So imagine the server computer sitting somewhere far away, and then it's connected to the client using this link, which is essentially like some kind of a network. And there may be like more clients sitting there which are accessing the same data. And essentially, like I mean, so when the client tries to access the flat file service, essentially, like I mean, it just associated this and directly, like I mean, it collects the data and sends it to the client. And it's almost like, I mean, you can think of here the client computer is accessing just as a one-on-one with interacting with the file services. So there is a directory service and a file service, and basically like the flat file service collects that file information and sends it to the client. So essentially, in a flat file service, all the files are assigned a unique file identifier or UFID, and so since the files themselves are uniquely named, it's easy to actually obtain what the file is. And essentially, like I mean, so one system that is accessing one of the files, the other systems may not be able to access that same thing. Every file has a unique identifier, and the clients need to know that unique files identifier in order to access that flat file. So the client, there's a client module that exports the interfaces by the flat file and the directory services from the server side. So the directory service itself, it's provided, it provides the mapping between the text names of the files and their UFID. So the client may obtain the UFID of a file by coding its text name to the directory services, and these are all like one-to-one mapping. So that's the uniqueness of the flat file service, which is not very interesting. And as you can see, actually the UFID can be a long sequence of bits because we need to map all the files in the file system with unique identifiers, which is kind of an arduous task anyway. So the client module, that is another piece of the services that we saw in this picture. This runs on each computer and provides an integrated service or a flat file service, because this service is pretty much constant or same across all the clients. So the client service, in fact, in the Unix side, actually emulates a full service, full set of Unix file operations. These are the operations that we saw like earlier, like open, close, and all those things. All of the services are provided by the client module. It also holds the information about the network locations of the flat file and then the directory server processes, so that it can actually go to those directory servers and access those files very easily. It achieves better performance through implementation of a cache of recently used file blocks at a client. So we can improve the performance of client module by having a cache, a local cache within that particular client in the system, where we store the recently used file blocks. Again, the issue will be how do we maintain the consistency, and so we will talk about that. So here some of the again commands that we can use. The read field I, n, and then that goes into data, essentially, like so it's a dash and arrow data. Here essentially, like we read a sequence of 1 through length of file, and this variable is I, which is essentially like we increment that, and then basically like when and then essentially like when that particular items are stored in data. The right field I data, essentially it writes a sequence of data into a file starting at item I and extending the file if necessary. And create is another command that creates a new file with length 0 and delivers a UFID to the field variable. And delete field just remove that file from the file store. Get attributes field, and then we can store it into another variable called attribute. And then set attributes, essentially like that's essentially like whichever attribute that you specify is set to that particular field, which is essentially the file ID, which is the unique ID that we have found out. So again, the access control. So in the distributed implementation, access write checks have to be performed at the server. So it's not a client that provides the access control, because the remote process control interface is unprotected point of access to all these files essentially. So until you reach the server, basically like it's all unprotected, and then basically like so the access control itself is provided at the server side. Directory service interface, essentially like that we will look into it now. So here there is a lookup for particular directory with the name, and that returns a file ID. And if the name itself is not there in that particular directory, then it throws an exception. So that is the throws not found field. The add name essentially like adds the name and call the file into that particular directory. And if there is already that name exists, then it throws an exception. Unnamed directory name is essentially like if the name is in the directory, then it is removed from the directory. If it is not there in the directory, then it throws an exception. And then finally the get names directory with pattern, get the text names in the directory with a match of the regular expression pattern. We will learn about regular expression in the future modules in one of the programming modules, and then that is assigned to the main sequence essentially. So now we go into the next file service architecture, which is hierarchical file system. So right now we looked at just the flat file, which is very easy to implement, very easy to access, but at the same time you cannot do a lot of functionality there, and also you need to carry a long unique file identifiers, which just causes issues by growing your directories and growing the client modules. Now let's go into the next one, which is the hierarchical file system. This essentially like is the file system where the directories are now arranged in a tree essentially. So essentially like you need to go into like various directories in order to figure out what is going on. And then also the file group is another concept there, where it's a collection of files that can be located on any server or moved between the servers while maintaining the same names. So we saw some of these examples when we originally started Linux. A similar construct is used in a Unix file system. It helps with distributing the load of file serving between the servers. So essentially, you can move the file system or the file group to be closer to where the client is asking for. So we can move to one of the servers. Also, the file groups have identifiers which are unique throughout the system. So that's the way that it can be moved from one system to the other. So here is one method to construct a globally unique ID. So we just use some attribute of the machine on which it is created. So basically, like the IP address. So we know that IP address is a 32-bit or a 4-octet binary. We just add a date to it, like so the IP address followed by date. We call it as a unique identifier. The date could be a date and time all the way to the second. Then the file gets created. So now we go into the distributed file system. So again, the three hierarchies that we talked about, or the three different types of file system that we talked about: the flat files, the hierarchical files, and now we go into a distributed file system. So here we will talk about two main file systems. One is the NFS or the Sun NFS. This was developed by Sun Microsystems in 1985. It's most popular and it's open file system, and it's used pretty much universally today. Also, the NFS protocol itself is standardized through this particular standard. It's known as the RFC 1813. So the main idea is here is basically the server or the file system itself is a stateless system. So essentially, the server itself is not required to remember anything, so it does not have anything in the memory. Essentially, the things like which clients are connected, which files are open, things like that. So essentially, it just the file system itself is sitting in one place. The clients basically send some requests essentially with all the information that are needed, and then basically the server just fulfills the request, and then it forgets the minute it fulfills the request and then moves on. So the onus is on the clients to provide all the information that are needed for accessing a file, or essentially to provide that or to get that service. So the whole so the advantage of this kind of a system is that the server state does not grow with more number of clients. So there is no change to the server itself, which you need to change the number of servers. And then the other key idea of NFS is when you perform an operation, and if you are repeating the operation, you get the same result. There are no side effects. So essentially, if you say like A equal to B plus 1, and then essentially every time you do the A, basically it always you get only A equal to B plus 1, or you don't get A equal to A plus 1, where now the state of A is different, so that the next time when you query it's a different answer. The second system that we will study is the AFS, or the Andrew file system. This is developed by the Carnegie Mellon University as a part of the Andrew Distributed Computing Environments in 1986. So you can see that actually they are fairly close. This research project was to create a campus-wide file system, and basically a public domain implementation is available on Unix. It's called the Linux AFS. So this was again also adopted as a basis for the DFS system, DFS file system in the Open Software Foundation, and the Distributed Computing Environment group essentially. So let's look at the NFS architecture. The NFS architecture consists of again the client computer, but as I mentioned, the client has a lot of onus on providing the data. So let's look at first the server computer. Server computer has nothing but a virtual file system, which holds the Unix file system, and then it has an NFS server, which is another program that serves the various clients. And then in the client computer, again, like you have the same kind of things. There is a virtual file system which has the Unix file system, and then whatever the extra ones here, basically the blank ones are various devices / devs. And then there is also an NFS client. The NFS client talks to the NFS server basically and provides the information as to what the files that it wants to retrieve or to write the content into that file. These programs actually they all reside under the Linux or the Unix kernel. So the communication between the client and the server are using RPC, what is known as the remote procedure calls essentially. So the client itself, basically it's a transparent access to the NFS file system. So when you go through this NFS client to the NFS server, since it is stateless, basically like it's as if like this is now connected together and there is no NFS server and NFS client, and basically it's just you can transparently access whatever is inside the Unix file system, the server side as well. So the client's job is essentially like to basically provide this file system and also the transparent access to the NFS. It also provides some virtual nodes essentially, which is essentially like procedures for procedures on an individual file, or it's an interface for procedures on an individual file. And then basically it translates that the individual file procedures into the various NFS remote procedure calls. So that way, like it can access the NFS server and retrieve that file. So here, essentially, like the application program provides the Unix system calls through the Unix kernel, and essentially, like the operation zone. So the virtual file system just keeps all the operations as a local operation, so you won't feel that actually there are some remote files also. So from the application side, you are just calling a local program, but the virtual file system identifies which is the local and which is the remote files, and then the remote file is channeled through the NFS client, and then it provides this RPC into the NFS server to retrieve that file. So the file identifiers, we already introduced this concept of a file handle. The file handle is the file identifiers that are used in the NFS itself. So here a particular file handle denoted as FH could be the file system identifier, the node number, and then the inode generation itself. So all of them are combined together to get to the file handle. So the various commands are used here. So in this one there is a read operation. We again, like very similar to the flat file access, give the file handle or the file ID, the offset and the count, and then that retrieves the data and then put it in the data variable. The write, for writing, basically we give again the file handle, the offset, the count, and then the data, and then basically, like, I mean, it is written into that file system, and then basically like there's an attribute that is written. The create command, essentially where we specify a directory file handle, the name, and then the attribute, and this command returns a new file handle and also some attribute on the file. And then the remove actually is remove just returns the status, essentially, like whether it got removed or not. Again, we give just the directory file handle and then the name, file name. The get attribute file handle gets the attribute related to that particular file. Then the set will set that. Then there's a lookup command, essentially, which returns the file handle and then the attribute. Rename command, it's basically the original name or the from directory file handle and the name to the to directory and then to name. Link provides a link to the existing file. Then the reader essentially reads a particular directory and then returns all the values into this variable entries. Symlink is a symbolic link, essentially, or a soft link, which ties a file to another and new name, and then that returns just the status. The read link file handle, essentially, like that returns a string, essentially. So it gives the expanded link path. Make dir is it creates a new directory, and for that it gives you the new file handle and then the attributes. And then rmdir basically removes a directory, and then stat file system file handle gives the file system status, essentially. So these are some of the commands that are used in the Sun NFS, which is one of the very popular systems. So now let's look at some of the other features of Sun NFS. In fact, we learned about this one. One is the security, or how do we make sure that there is an access control and authentication. So as I mentioned earlier, the NFS server itself is a stateless server, which means that the user's identity, access rights, all of them are controlled by the server only on the request, and essentially the client is so the local file system, they are checked only on the file's access permission attribute. So essentially, like, I mean, this is we have to check every time whenever we access the file system. So it does not remember, like, I mean, if particular user is authenticated or not. So every time we need to check again and again. Also, the client request is accompanied by a user ID and a group ID. These are inserted by the RPC, the remote procedure call. We talked about this also, like earlier, like in this example, where the virtual file system converts, or basically like it forwards the remote access to the NFS client, which converts the file handle into the particular remote procedure call, which contains these additional data, which is the user ID and the group ID, and then it sends it to the file system to gather that file. So the Kerberos is also, it has been introduced, it has been integrated with NFS, and that provides stronger and much more comprehensive security. So now let's look at the mount service. Mount service is used to mount a particular disk into the file system. So if it is a new disk, we use the mount function to do this, to mount the remote files. So the operation is mount, remote host, remote directory, and the local directory. So it basically like mounts that file system into the local directory. So in this example, the server maintains the table of clients, whichever ones mounted the file systems at that server. Each client maintains a table of mounted file systems holding the IP address, the port number, and then the file handle. The remote file systems may be hard mounted or soft mounted in a client computer, very similar to the soft link or hard link. So here another example where it shows the two remotely mounted files. So in the server there is a directory called people, which contains like Big, John, and Bob. In the client side there is a directory called user, which has students, which are remotely mounted on people, and then there is also another directory called staff, which is remotely mounted on staff in actually in users in server 2. Then there is also a concept of auto mounter. The auto mounter was added to the Unix implementation of NFS in order to mount a remote directory dynamically whenever an empty mount point is referenced by a client. So this is kind of if the client asks for a particular node which is empty by default, then the auto mounter automatically mounts the particular remote directory there. So again, the auto mounter has a table of mount points with the reference to one or more NFS servers listed against each. So it sends first a probe message to the each candidate server, to see whether the particular mount point is still available. Then it uses the mount point to mount the file systems and then serve the accordingly. And usually the auto mounter keeps the mount cable to be very small. So this also provides a form of replication for read-only files. So let's look at the caching essentially. Like so caching can be of two forms. One is a server-side caching, and then also the other one is the client-side caching. Before we go into the server-side caching, let's look at the client-side caching. The caching always is it provides improved performance because certain blocks if you cache, and basically those are the frequently used blocks, and if the client requests that every time, the cache can provide very quick access to that particular block, so that the system that is requesting that is not starving for data. So for reads, essentially, like so the always the protocol from the client side is checks with the local cache before it goes into the server, because whenever we go into servers it can take longer time, whereas the local cache will be easier. So only if there is a cache miss it goes to the server. But at the same time, writes basically you can the most or the Sun NFS itself provides a periodic write back and not an immediate write back to the server. Mainly the reason is we don't want to contact server that often, because that can slow down the communication network. So the client caches two types of data. The one is the data block itself, and then the other one is the attributes. Now let's look at the server caching. Basically, so the server caching is very similar to the Unix file caching in the local file. So the various blocks from the disk, they are held in the main memory buffer cache until the space is required for newer pages. The read ahead and delayed write optimizations are also possible. So what this means is basically so if you know that actually you are reading it from one particular file, instead of getting the portions that are in the read operation, you get more thinking that maybe like you can read ahead of time itself. And then delayed write is essentially like so you delay the write with either the various cache consistency protocols, and so that we can further optimize the overall caching mechanism. For the local files, the writes are deferred to the next synced event. So this is again the delayed write principle. So 30-second intervals is when like the synced event happens. The way the Sun NFS works very well with the local context, where files are always accessed through the local cache. But in a remote case, the synchronization, like it doesn't guarantee the necessary synchronization to the clients. So the NFS version 3 servers offers two strategies for updating the disk. One is the write through, and then the other one is the delayed commit. I think like you already know about this when if you had studied the cache coherency protocol, how to maintain coherency in a cache. Whereas the write through is essentially like you're writing it both in the cache as well as in the main file. In this case, essentially like so the altered pages are written into the disk as soon as they are received at the server. So then the other one is the delayed commit, whereas the pages are held in a cache until a commit signal arrives, and then basically at that point the the file system itself is written with the new data. So we looked at this one basically, the client caching. So again the client caches the results from the read, write, get attribute, lookup, and then the reader operations. The synchronization is not guaranteed when two or more clients are sharing the same files. So that's something that we pay the penalty for. Then the validity itself is checked through a timestamp based check. Essentially, like it reduces the inconsistency, but it does not eliminate it. So it's used for the validity condition for cache entries at the client. So the formula is like T, which is the current time, minus TC, which is the time when the cache entry was last validated, must be less than T, which is the freshness guarantee. So we don't want excessive time pass between these two events to do anything kind of thing. And then essentially the TM client is the time when the block was last updated at the server, and then basically TM TM server is essentially like when so actually TM client is the time when the block was last updated at the client, and then the same thing is when it was updated at the server. TC is the time when the cache entry was last validated. So so basically, like I mean, we need to make sure that this is the validity condition that is satisfied for the cache entries. So in the previous one, the T itself is it's the freshness guarantee. That can be customized, so you can decide what that value should be, and then based on that we can construct um, the rules. So the T is set between like 3 seconds to 30 seconds. Also, it remains difficult to write distributed applications that share files with the NFS itself. So one other question that may come up is how do we maintain how do we update, or how does client update the server? So for files, essentially, like I mean, we can do the write back from the client cache to the server, and then we can decide that interval as 30 seconds. Also, like there are commands called flush on close, which is essentially it takes the memory reads and writes and then push it into the file system automatically. For the directory, is essentially like we just synchronously write to a server. So as an example, we can say, like, okay, the client X and Y, they have a file name called A that is cached, and then the file name A occupies the blocks 1, 2, and 3. So now the clients X and Y both can open A, and then X writes to the blocks 1 and 2, and then client Y actually, like now it writes to the block 1, and 30 seconds later what happens? The client Y reads block 2, and 40 seconds later the client Y reads block 1. So again, like I mean, this is one scenario, like I mean, where you can find out how system will behave. So the performance itself is another parameter or another concern that we talked about. So the write operations is only like I mean responsible for 5% of the server calls in a typical Unix environment. The lookup accounts for 50% operations because step-by-step path name resolution is necessitated by the naming and then the mounting semantics. So the recent measurements show a higher performance of the Sun NFS, and then the last measurement was taken in 1993. So in summary, NFS is an excellent example of a very simple but a robust high performance distributed service or a distributed file system. So the access transparency essentially, like I mean, for the same Unix call is or the Unix call itself is same for both local and remote files. So that is one of the things we talked about in the transparency. So let's look at those the transparency in detail. So the location transparency, the naming of the file systems is controlled by the client mounting operations, but the transparency can be ensured by the appropriate system configuration. So even though like I mean the client actually controls the mount operations and how to name the files, the transparency can be controlled if you actually configure the system with the appropriate information or uniqueness in the mount points. So mobility transparency essentially, which means that when the system is changed from one to the other, how do we ensure that transparency? This is not achieved at all, and relocating the files is not possible, and only the file systems are possible, but that requires an update to the client configurations because clients are the ones deciding everything about this particular file system. The file system itself is memoryless. And then the scalability transparency essentially, like I mean, so again this one we can subdivide the file systems and allocate, and we can allocate separate servers for each of the file system. So that way, like I mean, we can scale the system, but it's also depends. The performance itself is determined by the load on the server holding the most heavily used file systems. Replication is another one. So for replication, since we do a limited only we limit this file system to read only file systems, basically the replication transparency itself. So for writable files, the Sun Network Information Service or the NIS runs over NFS, and that's used to replicate essential systems. The hardware software operating system heterogeneity, again the NFS has been implemented for almost every known operating system and hardware platform, and that is supported by a variety of filing systems or filling systems. Fault tolerance, it's limited but effective. So service is suspended if the server fails. Recovery from failures is aided by a simple stateless design. And efficiency, basically it can be implemented for use in situations that generate a very heavy loads. So the next case study will be the Andrews file system. Before we go into that, I also want to talk about a little bit on the Sun NFS file system. So the key takeaways that you want to take away are number one is it's a stateless server, and then the operations themselves are what is known as the idempotent operations. So what I mean is here. Oh, where is it? So yeah, and then the other takeaway is also the client so so yeah, so the idempotent server operation is essentially like, I mean, so when you repeat an operation, it does not have any side effects. So it also helps with the various other things, basically like the fault tolerance, the scalable performance, the consistency. They are all addressed in the NFS system. And then one thing to note is when particular system crashes, it tends to slow the server to the other clients, the clients that are there. So this is kind of one of the drawbacks of the system, you can think of it. And then the client also like needs to cache the data for scalable performance. Not just the server alone needs to cache. In fact, when server caches, sometimes it is not meaningful. And since we put a cache in the client side, the data consistency is extremely hard, because now we don't know like which copy is the latest one, because there is some other copy that is still sitting in the process itself. So that's all I have for today. We will continue from this point next week, then we'll do in the next class. Thank you very much. Sandeep.